So what we thought we'd do for this session is first I'm going to do a kind of quick and quite basic introduction to some of the issues of sampling bias that might affect standard molecular epidemiology analysis, kind of when you're drawing phylogenies, basically one sample per host typically. And then Ollie and Xiaoyue are going to go on to talk about the specific issues surrounding phyloscanner, where the tree is a bit hidden, and what you've got out is more a set of transmission pairs, and you want to adjust for possible sampling biases in selecting those. Okay, so to quote Wikipedia, where I went to for a go-to quote, sampling bias is a bias in which a sample is collected in such a way that members of the intended population have a lower or higher sampling probability than others. And in more traditional epidemiology and just general population surveys in general, it's usual that the characteristics that you're interested in, the characteristics of the individuals you're sampling. And in that case, sampling bias is a well-known problem, and methods for adjustment for it are well established, such as weighting by demography. But the thing about molecular epidemiology is part of the reason we do it, and maybe the primary reason we do it, is that we're not just interested in what our sample tells us about themselves, but what the sample tells us about the history of the population. That's what the tree is. It's drawing a kind of a reconstruction of the ancestry of our sample. And using that kind of thing, we look at who infected who and past population dynamics and so on. So it's not just our sample we're interested in, it's also the history of our sample. And sampling bias can also affect the inference of that history, even if the sample you've taken is entirely representative of the target population. And the effect of sampling bias on this kind of analysis are perhaps not quite so well studied. So I was thinking about this, and I thought there were kind of maybe three particular problems when it comes to sampling bias in phylogenetics and pathogen phylogenetics. Firstly, the idea that everyone is connected, or all the lineages are connected. So the lineages you take in your sample will almost always have ancestors that you could never have collected. And those ancestors, you might never have collected them because they were somewhere that you didn't sample, or they were sometime you didn't sample. They're the two basic places you might be missing. And those may have very different characteristics. For example, if you're sampling in one country and you have lineage importations from another, which you never sampled, then you've got no way of finding those lineages. Another problem is you can't usually go back in time. You need to get a sequence. You're going to have to take a biological sample during infection, and you can't. If there was a period where you weren't performing sampling, then you can't just go back usually and retrospectively case find them, because they may not. The information you need is not going to be present in a lot of cases. Infections will clear for some pathogens, or people will move, or people will die. And there's also the problem that background data that you might use to try and fill holes when you're doing a prospective study can be quite patchy. Routine genomic surveillance has often not been performed, or it's got much better over the recent years, but it's still quite patchy in a lot of locations, and what's available may not be representative. So I'm going to now go through some toy examples of the kind of ways these can affect things, assuming this is a kind of a phylogeography analysis. So we have a tree on the right here. We kind of assume it's a time tree. So this is kind of the calendar ancestry of a set of samples at the tips, which are taken from 4 locations labeled A to D in the 4 colors. And the first tree you get out there would be just one that labels the tips by location. And we've taken samples there and built phylogeny. And we're doing this because we want to look at not just what happens at the tips, but what happens deeper in the tree, at the internal nodes in the tree. And so there are various different models to look at this, but basically all of them will in some way involve a procedure that will assign states to the internal nodes of the tree. So for example, if you did this is just a parsimony reconstruction. If you did a parsimony reconstruction in this tree, you'd get the idea from this that green was the ultimate origin of the lineage in this tree, which is location C. But suppose that you didn't sample C. Suppose you only went to the other 3 locations and took samples from them. And so the green in this, it's the same tree, but the green nodes are faded out. So in this case, then the reconstruction algorithm you've used just doesn't know about that location at all. So you'll get a tree like this. The green ones have gone, otherwise the branches are the same. And if you did the reconstruction procedure in the same way, you get something erroneous, because it only knows about the information it has at the tips. And without that information, it can't make the correct inference. So a couple of things to do if you're worried about this. Firstly, I mean, a good procedure generally is just try and find background sequences from publicly available databases, from GenBank, from Los Alamos, to try to fill the gaps. There's also some things, kind of patterns that are quite suspicious. So on the right here, so we have two clades which are joined by very long branches. And supposing we were sampling over that entire timeline, we didn't just start sampling about halfway through, we were sampling the whole thing, we've still got these long branches. Since sampling was going on at that time, it kind of suggests that it was going on somewhere you weren't sampling, because if those lineages were in your study area, you would have found them. So patterns like this are quite suggestive of an importation from a location you haven't managed to sample. It's not just a question of missing a location, however. There's a sort of question of how many samples you take from each location. So this is another tree, and the reconstruction, the parsimony reconstruction, which I'm just using an example, there are quite a lot of methods you can use to do this, suggests that the implications come from location A. However, suppose I remove half the tips of all the locations except C, then you get another tree. You know, it's the same one, just taking away those ones. And because C is overrepresented in this tree, you get C as a reconstructed origin. Solutions to this. So if you can, in the first instance, try to even out sample counts between locations and see if that makes a difference at least. But you're always limited by how many sequences are ever collected. If you have a very, if you have a very rich data set, that's a good procedure to go by. You don't always have that luxury. There are also more sophisticated models of inference that can help with this kind of problem. So the general linear model, discrete traits variant, which gives you a predictive of significant demographic predictive of spread between locations or between other populations, allows adjustment for sample counts when trying to identify them. And also the structured coalescent models, which are a variant of model of movement between discrete populations, are generally less prone to this problem than the ones than parsimony or the continuous time Markov traits discrete trait model, the LeMay model, for people who know about that. Moving on to the problem I mentioned earlier about gaps in the timeline. So we have a tree here where you can see close to the left in the early chart of a timeline, most samples were from the location B, which is then reconstructed using the algorithm as the origin of the tree. But if we didn't collect those samples at all, if we only started sampling halfway through, and you take those ones away, those fade out, you get a tree like this. And then that whole suggestion you had very clearly that there was something going on in location B in the early timeline, you miss that, and you'll get a kind of very mixed and matched reconstruction of this tree in particular. Solution to this one, again, background sequences of older studies can potentially help, so we'll get on to some issues of that later. They may not be collected, they won't have been collected using the same sampling frame that you might select, so the caution with users. But there may just be no way to acquire the needed sequences. So just be careful with this, and just don't assume that your software necessarily knows what it's doing. Look out in particular for the situation I had back here, with the long branches, which may suggest if the sampling frame is late here, if you're not sampling over the whole period, that suggests there's evolution going on at a time you can't really see. And lastly, the question of what I might call overly influential reference sequences. So the use of just trying to find other relevant sequences to add to your analysis is good practice, but it's not foolproof in its own right. It can have pitfalls. So right at the bottom of this tree, you have two purple ones. So um, supposing this is what you sampled. So you have from some previous study, those two samples were added to say GenBank, but your study proper started a bit later and the faded out tips there are not available to you. So that's the reconstruction from the full tree, which is blue then red as kind of the big sort of backbone lineage of the tree. But if you were to just cut it so you had the tree that I said you have access to, then those tips are very influential, more than they should be. So in summary of this, sampling bias in phylogenetics is important to consider. The shared ancestry of the samples raises questions that traditional epidemiological studies need not address, and missing samples in space and time result in erroneous inferences. Using background sequences from e.g. Los Alamos or GenBank can help give context to sequences you collect respectively. That's not foolproof, and these likely problems will lessen as sequencing becomes more widespread. So for example, European HIV epidemics are now quite well documented in sequencing databases.
I would like to continue on the start that Matthew how Matthew started the session, and talk a little bit more about deep sequence phylogenetic analysis, and when we go to quantify transmission flows, and then what impact these sampling biases might have, and so what do we actually want to do? So we want to help address some of the central questions that underlie HIV intervention policies. And one of them is like, which population groups are the main sources of new infections? And so we're interested in these sort of questions. And an example of that is in terms of geography. Are there particular areas with, say high HIV prevalence? Like if you look at like these areas here, around Lake Victoria, or if you go down towards South Africa, you can see there's these areas of high HIV prevalence. Are these sort of the sources of infection in neighboring areas? So that's one of the questions we've considered already. Another one is concerning age dynamics. For example, are men who are 5 years older than the women, are these the main sources of infection in women, and especially among young and adolescent women? So these are sort of like two examples of groups that may drive onward transmission, and we'd like to quantify that. And so the way we've started to think about this mathematically is like to think about things. So these are population groups, not individuals, but population groups. That are at high risk of infection, so they would have a lot of quantitative inflow or sources. These are groups of individuals that are at high risk of infecting others in terms of the proportion of transmissions going out from them, and hubs that are both. And you know, thinking about this mathematical concept and how do we translate this into numbers. So we think about directional transmission flows. So I made this really simple to start with for the explainer session. So let's just think of two groups, population groups. One of them is living in a high prevalence area and the other one is in the low prevalence area. So you get 4 possible flows from individuals living in a high prevalence area infecting others in the high prevalence area, and then from low to high, high to low, and low to low. And the point with these directional transmission flows is that they sum to 1. And we can make this more complicated. We can, for example, think about male to female transmission or female to male transmission by different age bands. So we have a much larger flow matrix where in the upper block matrix is male to female and the lower one is female to male. And then the 1 to capital K, they indicate different age bands. So for example, 18 to 24, 25 to 30, and so forth until maybe 45 to 50. So these are much larger objects now, so much larger matrices. And again, all these flows, they sum to 1. And we'd like to estimate them and have an idea about how the sampling processes that underlie our sample that we're looking at, how they may have influenced these estimated quantities pi, which are the directional transmission flows. What are we really interested in when we look at these this flow matrix pi? We're interested in, and this is terminology now, the sources. So we keep a recipient group fixed, right? So we might be looking at flows into low HIV prevalence area, and we ask what are the sources of these. Conversely, we'd be interested in who's transmitting onward. So if we keep the from population group fixed, and we ask who are they transmitting to. So these are the onward transmissions. We can also look at the flow ratio. So if we look at say this group here, so this could be I have it this way around. So say from well, it's a kind of complicated matrix, but if you just think of a 2x2 matrix and go back to our very simple example, then you will see that this keeps reoccurring in the talk. So we had the individuals in the low HIV prevalence community, and the question is, what proportion of these is infecting individuals in high prevalence areas? And here on the other side, it's just the other way around. So from high prevalence areas to low prevalence areas, and we can take the ratio of that. So this is essentially the flow ratio, and it's another important statistic that we're looking at. So these are kind of like 3 important statistics that we want to derive from this flow matrix. And one example that we've looked at in the past is we looked at the Rakai area, which is located about here. I hope you can see my mouse. And we looked into the question whether low HIV, what are the transmission flows between low HIV prevalence inland communities and high HIV prevalence fishing communities that are just at the shore of Lake Victoria. And we were really interested in this flow ratio. So in the flow ratio of transmissions between hotspots with high HIV disease burden and neighboring areas. So that's where I personally spent a lot of time at over the past few years, I'd say. And when we look at the just the raw data, so we do our phylus canal analysis, we get our highly supported transmission pairs, and we just count them. So and what are we counting? So we had here an area which is the lakeside area on Lake Victoria, and we had 4 fishing communities where the survey was undertaken, and from infected participants in that survey, samples were obtained. So, where's my mouse here? There we are. And so we were looking at these 4 fishing sites, and we had individuals sampled from these locations. And then the Rakai Community Cohort study also looked further inland. So there are several other communities that are under surveillance. And here again, from infected individuals, sequences were obtained. And then we did our phylogenetic analysis with phylus canal, and we asked, okay, so how many transmission pairs do we see? How many do we see that have a source and a recipient, phylogenetically likely source and phylogenetically likely recipient in the low prevalence area, in the high prevalence fishing communities, and between them? So what we found is that there were 94 within low prevalence inland communities and 141 within the high prevalence fishing communities, and 23 went from the low prevalence inland communities to the high prevalence fishing communities, and much fewer the other way around. So that was talked about this before. This came as a surprise. But today I want to focus on the issue of sampling biases in a bit more detail. So there, as you can imagine, there's probably like many different sampling biases that are, underlying the data that we're looking at. But just to raise sensitivity to this issue, so you can look at population density in the area under surveillance, and you can see that generally there's more individuals living inland compared to at the shores of Lake Victoria. And in fact, like if you just, well, it's a bit hard to see, but essentially in the survey, the primary locations and settlements where individuals lived at the lakeside, they were included in the survey. But you can see from this map that this isn't necessarily the case, further inland. So we have this kind of bias that essentially at the lakeside, all the big population centers are in the analysis, but further inland that was not the case. On the other hand, HIV prevalence is much higher at the lakeside, and we can also calculate the number of individuals living with HIV per square kilometer. So you get the sense that the sampling was, in terms of the populations that live either at the lakeside, which is shown here in orange, or the inland area, which is shown here in green, was quite uneven. So when we with our best attempts, when we tried to adjust for these sampling biases, with the method that is in the Lancet HIV paper, just to give you the sensitivity of what impact that has in our estimates. So we're now, after adjusting for this fact that we are not having all communities in the survey in the green inland area, and when we adjust for that, we estimated 88.7% of transmissions occur in the inland area. So that's, we need to compare this to the 35.5% up here, and correspondingly, the estimated flows that occur in the lakeside area are just 5.2% compared to the 53.2% of transmissions within the raw data and the raw sample. That didn't change our conclusions about the direction of transmission. So I just wanted to use this example to show you that adjusting for potential differences in how the sampling was done in these locations may have quite an impact on what you infer quantitatively in terms of these transmission flows, and potentially also the flow ratio. In our analysis, we could show that thankfully this wasn't the case, but there's always this potential, and we probably want to be mindful about this and be aware that these sampling processes and how the sequences we obtain from the population can potentially quite substantially influence our inferences. And we have prepared a little hands-on example for you, which Xiaoyue is going to talk more about just now.
I will go through a small example to give you a sense how the sampling differences would lead to the bias in transmission flow estimation. Consider we just have two populations, and the 1 and 2, and you can say the actual transmissions in the first matrix. The transmission, for example, the transmission within group 1 is 50. Those within group 2 is 20. From 1 to 2, the transmission is 10, and from 2 to 1 is 20. Assume that we can sample all the individuals in group 2, and we can only sample 60% of people in group 1. Then the question to think about is what are the average observed transmissions within and between these two groups, and what is the true transmission flows? And if we are only given the observed transmissions, could we estimate the flows, and what are the estimates for the flows? And you can use the package in R to calculate the binomial confidence interval.
What we have in mind is, like, there are 4 questions, right? So based on these these numbers that you see on the screen. So the idea is, can you as a group calculate the true flows? So what's the proportion of actual transmissions? So these should be 4 proportions and they should sum to 100%. So that's the actual transmissions. And then applying the sampling and assuming that in individuals in locations 1 and 2 are sampled independently with these probabilities 60% and 100%. Can you fill in the similar 2x2 matrix on the observed transmissions? And then can you again calculate the flows, so the proportions? And what we will do is, like, we will try and hop into a few groups and see how you get along and if you got any questions. And we'll probably do this for, I don't know, 6 minutes or 7 minutes and then see where we are. Shall we try that? Will kindly agreed to talk a little bit about what our group did.
Hi, Ollie, and everyone. Hey. Yeah, so we sort of, we looked through what are these numbers of observed transmissions going to be? So I guess the most straightforward case is if we're sampling 100% of site 2, then we should see all the transmissions from individuals in site 2 to site 2. So that if we had this 2x2 matrix, then the bottom right-hand value of the observed transmissions will be 20. And similarly, we can sort of use the same idea to sort of fill out the other numbers. So we should observe 100% of transmissions in 2, but from 2 to 1, since we only observe 60% of those, we should get 60% of these 20. So from 2 to 1, we should get 60 of them. So we should get 12, see 12 of those. And then from 1 to 2, 60% of those. So 60% times 100% will give us 6. And then from 1 to 1, we're seeing 60% of individuals, well, 60% from 1 and 60% to 1. So 60% times 60% will give you 36%. And so 36% of 50 will give you 18. So we have a 2x2 matrix of numbers of the observed transmissions. And if we calculate those as a proportion, and we just add them up and divide each of them by I think the total is about 56 or something. So you can calculate the estimated proportions, something like that. Thanks,
that's great. Thank you. Thank you so much, Will. Just to wrap up what Will just talked us through is that, when we start with these actual transmission, of course, this is hypothetical, we don't know them, and we assume a certain sampling process, and what it's much lower in population group 1. We only are sampling 60% of individuals, but we're seeing everyone in population group 2, 100%. So the question is, like, if you just apply this forward to sampling, assuming we know the truth, what would we see? And so this is essentially 18 from 1 to 1, 6 from 1 to 2, 12 from 2 to 1, and 20 from 2 to 2. And we can, using binomial confidence intervals, we can work out the proportions. And you can see, like, that, if you're looking at transmission from 1 to 1, it's actually 50%, but binomial confidence interval doesn't even include 50% as doesn't even capture that. Because if you just apply binomial confidence intervals, there's no way to adjust for uneven sampling. And similarly, like, you're overestimating the proportion of transmissions from 2 to population group 2. So you're estimating it's 35.7%, but in reality, given these values, it should be 20%. So hopefully this gave you a bit of appreciation that these sampling biases can have a substantial influence on what you're estimating in terms of transmission flows. And based on these simple examples, we've got a bit concerned, and then we started, like, the work that we've done, and then that Xiaoyue has led quite a bit on just working out methodology to try and correct for these sampling biases.